Welcome to a presentation of EDAptability's RTL to RTL partitioner. My name is Tobias Strauch and I would like to thank you for listening to this presentation. The best way to present software is to run you through an example, but before that we would like to outline the key benefits of this new tool. The RTL to RTL partitioner is not only a tool, it also has an impact on the system prototyping flow and the methodology. On the left hand side you see the old EDIF based flow. The complete design is synthesized first and the resulting EDIF netlist is partitioned into multiple EDIF files, and each EDIF file is then placed and routed on the individual FPGA. In the new flow, the tool partitions the RTL and dumps it in RTL in the original format again. Each individual RTL is then synthesized, placed and routed standalone. By the way, it is widely accepted that an RTL synthesis, place and route algorithm can work much more efficient and achieves much better results in a much faster time than an EDIF or netlist place and route algorithm. Well, ask Magma Synopsys or look what has happened in the last ASIC world the last decade. But the major advantages are that you can simulate the partitioned RTL with your original test bench, because the hierarchy and the signal names don't change. The new flow can handle incremental design updates much more efficient due to recent major tool enhancements of FPGA compiler like Simplify Pro and tools from FPGA provider like Altera. What I also really like as one who has spent quite some time with netlist based partitioner tools is that you don't need that monster machines with tons of memory for the very redundant database anymore. EDAptability's partitioner works with an extremely efficient high-level database and works on all standard PCs basically. EDAptability's RTL to RTL partitioner also inserts automatically pin multiplexing logic and memory wrappers in RTL format. If you are able to quickly run this through a fraction of your regression suite, you can make sure that the design modifications work fine and you don't have to debug it on FPGA level. Anyway, modifications for debugging, for example, can now be done on one single FPGA standalone. Only because you change one little thing in the system, you don't have to touch the complete RTL. You just incrementally rerun the synthesis, place and route of this particular FPGA. The third slide gives you an overview of how the RTL code looks like after partitioning. On the left hand side you see the original RTL code. We have assignments, processes and submodules. Each of the assignments and processes are handled as individual clusters. So assignments, processes and submodules can be individually partitioned into any FPGA in the system. The module of the original RTL code is then uniquified by adding a prefix to the module name. This happens also to all upper level modules as well, but certainly not to all modules in the system. It is important to notice that the instantiation naming remains the same, so the hierarchy path remains the same, except one additional entry on the top level, which is usually handled with an if-def statement. During dumping of the code of FPGA 1, for example, the assignments, processes and submodules which are not placed in this FPGA are then removed. After that, additional connectivity assignments of the routed signals through the upper level modules are inserted. So you keep the hierarchy of the original code and the original format, the comments and the readability. There are no limitations to signal types or to mixing Verilog and VHDL. After reading the design and the board files, this is what you see: a graphical representation of the board files and the chip top level. You now want to ungroup the chip to the individual sublevels at free will, but they should be small enough to be placed into individual FPGAs, of course. You will then see the submodules and the assignments and processes, which appear as clusters. All of these clusters and submodules are called elements. You can continuously ungroup submodules again. The ungroup command can also be issued later on in the partitioning process, and elements can be grouped together in any order again. You then drag and drop the elements into the FPGAs or black boxes like external memories for instance, and the information on the GUI is updated. You see the estimated FPGA utilization in terms of logic, registers and memory. You also see the number of traces between FPGAs. Also, the number of signals between FPGAs after placing, and the number of signals between FPGAs which have already been assigned to particular FPGA pins, and so on. Every command you issue is added to the action tree, which basically numbers the individual steps and gives you an overview of what has been done so far. You now can go back to individual steps and continue from there, issuing some other commands. And of course, you can go back and forth at free will and explore and compare various partitioning strategies. You can also dump one path in the action tree, so let's say from step A to step B as a script. So if you rerun the tool, you can redo this particular set of actions which you previously dumped. By the way, the complete tool can also be run in batch mode, and everything you do in the GUI can be done by script. There is also an integrated what-if analysis, which means a report is issued that tells you the results after the selected elements are placed in each of the FPGA. The routing frame on the left hand side lists you all signals between FPGAs. On the right hand side, the traces between FPGAs are listed. Traces are obviously the connections on the board. It also lists the signals which have already been assigned to traces. Each FPGA gets a unique number, so you can easily see proper signal-trace combinations. There is a wide range of sorting features and filtering features available. For example, you can have a look at clock domain specific signal connections if you want. If you select one or multiple signals and traces and press the routing button, the signals are then assigned to individual board traces and FPGA pins. Before routing, you also can define the signals which are used for pin multiplexing. Especially with the feature of selecting clock domain specific signals or cross-domain signals, the method pin multiplexing starts becoming very practical, and this partitioner sets a new standard. The partitioner dumps RTL pin multiplexing logic or inserts customer-defined logic. After each place and route step, the quick static timing analysis is issued. On the STA frame, you then see the timing histogram of your partition design and potential violations if you already have entered the clock domain timing specification. You also get a clock domain specific worst case timing report, including potential delays resulting from pin multiplexing. The partitioner has an integrated auto placer and an auto router. The auto router algorithm always gives the best results in terms of timing because this can be calculated very straightforward. The auto placer elaborates all possible solutions. The number of elements are limited, the number of FPGAs are limited, and so is the number of possible partitioning results. The auto placer will then report the 10 best corner cases, and you can select one of them. All these algorithms are extremely fast, since the database of the partitioner is extremely efficient. Another integrated algorithm that separates us from the competitor is the switch setting algorithm for hardware systems using switches for routing. The switching structure can be defined in a dynamic Verilog board description file. During the routing of the partition design, the switches are set or unset. This makes the back and forward optimization between partitioner and switch setting software obsolete, and creates the best possible routing structure for any switch routing hardware. We previously talked about dumping the modified RTL code. One important option is that the output files are only overwritten if the files definitely change, so only the new files get a new timestamp. This option is important for the incremental synthesis place and route flow. Finally, we need to mention that there is also an integrated memory wrapper generator. It basically suggests signals in the design which could be replaced by memories. If you select them, a wrapper is generated for the specific Altera or Xilinx memory. The original RTL is then modified for that. In the end, we would like to thank you again for your time. We hope you liked the presentation and you would like to know more about EDAptability's RTL to RTL partitioner. We would be very happy about any kind of feedback, and please drop us an email to feedback@edaptability.com. Thank you again and have a nice day. Goodbye.